Hi class, good afternoon. It's April the 20th. We've had our second test. Most of you have submitted that material. So we have 3 class meetings left. I'll be making announcements about how we're going to manage the final exam. So be checking your email regularly. This is one of 2 videos, I hope, for April the 20th. If the Gauss-Jordan elimination and quiz 5 is going well for you, you can wait until later to view this video, but this topic will be on the final exam. I'm not sure you've had enough practice with Gauss-Jordan elimination. I haven't given you an exercise set other than a very limited one. So I want to supplement that and also discuss an application. We haven't done an application for this material. There are extensive applications for linear algebra, but we don't see much of them in this course. The problem is that they are of such variety, and they need preparation to, in other words, to set the context. Takes a lot of time. You usually encounter these applications in other courses, but I feel like you should see at least one application, and there is one that can be presented without a lot of preparation. In other words, it's fairly easy to set the context. So what I want to discuss is curve fitting. Now, we all know that through any 2 points, there is one and only one line, and the algebraic way of saying that is if you have 2 data points with different x coordinates, there's only one linear function whose graph goes through those points. So I hope you recognize this as slope-intercept form, y equal mx plus b. The slope of the line is m, the y-intercept is b. So if you're given 2 data points, you learn how to do this in Algebra 1 in high school. You can work out what the equation of the line through those points is. We're going to go from 2 data points to 3 data points. So 3 data points determine a quadratic function. So quadratic functions have the form y equal ax squared plus bx plus c. If we're given 3 data points with different x coordinates, we can work out what these coefficients are using Gauss-Jordan elimination. I'll show you how it goes. All right, so here's the problem we're going to solve. So our data is this, our 3 data points. We'll denote them by P, Q, and R. So P has coordinates 1, 6. Q has coordinates -1, -12. And R has coordinates 2, 21. And our problem is find the values of A, B, and C so that the graph of y equal ax squared plus bx plus c passes through the 3 points. Points of P, Q, and R. Okay, so in engineering and science, including the social sciences, we have to fit functions to data. That's another example of modeling, and this is a simple instance of that. Okay, here's what we do, class, and this is for convenience. We're going to work with the template. And you won't see why we're doing this at first, but we're going to read this from right to left. We're going to say C plus XB plus X squared A equals Y. Why on earth do we do that? Okay, now remember, our unknowns are not X and Y. Our unknowns are A, B, and C. We're trying to find the values of these coefficients. Okay, if we want the graph of this to go through the point P, then if we let X be 1, we'll have to let Y be 6, and that gives us an equation. So point P gives the equation C plus 1 times B plus 1 squared times A is 6. And point Q gives the equation, so if we replace X by -1, we have to replace Y by -12. So C plus -1 times B plus -1 squared times A is -12. And then R gives us the equation C plus, so we're going to put 2 here and here, and we're going to put 21 here. 2B plus 2 squared times A equals 21. Okay, now let's clean these up a little bit. So 1 times B is just B, 1 squared times A is just A, plus -1 times B is the same as minus B, and -1 squared is plus 1, so this is 1 times A again. So here are the equations. C plus B, let me write it here, equals 6. C minus B plus A equals -12, and C plus 2B plus 4A equals 21. And now we see why we wrote the template down in reverse, because these are conveniently displayed so that we can do our Gauss-Jordan elimination. And furthermore, the simplest terms are on the left here, so when we do our clearing, that'll go rather quickly. One of the reasons I'm doing this, I wanted you to see an application, but I also have an exercise set that I can send you, and that'll give you extra practice with Gauss-Jordan elimination if you need it. Don't forget your quiz is due on Thursday. You have to submit it by Thursday. All right. So now you're free to use matrices if you wish. 1, 1, 1, 6, 1, -1, 1. I explained how that worked briefly last time. I'll just work with the equations themselves. So I want to clear this term and this one. I'm going to combine two operations now. So how do I get a 0 here? I need to add -c to c. I don't have -c, I have c. So I'm going to multiply by -1, in other words, -1 E1 plus E2 replaces E2. And I'll use the same operation to clear this term. So I'm combining two operations. Okay, so change the signs of these terms and then add to this equation. So when we perform this operation, the equation that changes is the one that the arrow points to. This equation is going to change. Minus C plus C is 0. Minus B minus B is minus 2B. Minus A plus A is 0. We accidentally cleared that one. We were just trying to clear this one. Minus 6 minus 12 is minus 18. This is our new E2. Now we're going to do this operation. So minus C plus C is 0. Minus B plus 2B is B. Think of it as 2B minus B. And minus A plus 4A is 3A. And minus 6 plus 21 is 15, I believe. Now, you might be inclined to use this equation to clear this term, but if you don't have to slavishly follow the algorithm. If you're thinking clearly, you should realize that this is already as good as a triangulated system. We don't need any more clearing operations. Why? This equation only has B, right? So we can solve for B. We can put the value of B here and solve for A. Then we can put those values here and solve for C. So this is not triangular, but it's just as good as triangular. All right, so let's finish then. Back substitute. So minus 2B is minus 18. Divide both sides by negative 2. So B is 9. So 9 plus 3A is 15. Subtract 9 from both sides. So 3A is 6. So if 3 times A is 6, A is 2. B is 9, A is 2. C, A is 2. C plus 2, I beg your pardon. I'm substituting in this one now. C plus 9, B is 9, plus 2 is 6. So C plus 11 is 6, so C is minus 5, right? Okay. So our answer is, let me write it here. So the quadratic function, now I'm going to write in the conventional way, y equals ax squared plus bx plus c. So y is 2x squared plus 9x minus 5. So This is a quadratic function. Its graph is a parabola. If you have a graphing calculator, you can display the graph. So it passes through these 3 points, and you can check that easily. You can check your answer easily. Look at the point P. When x is 1, y is supposed to be 6. Put a 1 here and a 1 here. So what you have is 2 plus 9 minus 5. That's 6, isn't it? Put a negative 1 in. This is now negative 9, and this is plus 2 because negative 1 squared is plus 1. So 2 minus 9 minus 5, 2 minus 14 is minus 12. Finally, 2 times 2 squared, that's 8, plus 9 times 2 is 18. 8 plus 18 is 26. Subtract 5, you get 21. So once you have your answer, you can check it. Okay, I do have an exercise set, and it does 2 things, at least I hope it does. We've now covered one simple application of Gauss-Divine elimination, and also when you work out the exercise set, it'll give you more practice doing Gauss-Divine elimination. Okay, don't forget your 5th quiz is due Thursday.